Okay, in the statistics lab, students are going to do a very simple experiment using nothing more than a ruler to measure their reaction time. And the purpose of this is really just to test the repeatability of a measurement, understand some concepts about statistics, and about measurement uncertainty. So the way this will work is one student will hold the ruler up while another student places their fingers as best they can tell at the zero line of the ruler. And as the first student drops the ruler, the second student will attempt to catch it as soon as they see it fall. Of course, if I do it myself, I have an unfair advantage of knowing when I'm going to drop it. And then they will record the position of their fingers on the ruler to determine how far it fell. Use the equations of freefall to figure out how long the reaction time was. And they will do that many, many times using both their left hand and their right hand in order to generate some useful statistics that they can compare. So the students will be comparing the data for the reaction time of their left hand to that of their right hand. It provides an opportunity to measure two things that should be the same, but due to measurement uncertainty won't have exactly the same values. So we'll have to use the concept of experimental uncertainty to say whether or not those values agree. So students will produce two histograms, one for the left hand, one for the right hand, of their data. And whatever the uncertainty is in their ability to measure the distance, that should be the units that they use for the histogram. So here I've assumed that my measurement uncertainty was 1 centimeter based on essentially the width of my finger. And so I'll group all my measurements, or I'll round all my measurements off to the nearest centimeter, and then plot values for the number of times that I recorded the different results. And I'll have an appropriate scale on the axis. And I'll do the same thing for the other hand. And from those histograms, students will determine the mean. Well, they can determine the mean directly, as well as a standard deviation. Using Excel, they'll plot those on the histograms. So the mean can be plotted. We see those means aren't exactly the same. So when we include the range from the mean minus a standard deviation to the mean plus a standard deviation, so this is x bar minus delta x, or since we're dealing with statistics, I'll write that sigma x, and this is x bar plus sigma x. If we do that for both histograms, we can ask if those ranges overlap. Okay, and so here it's clear that there's a region that is encompassed by both plots, and that means that the results agree within the experimental uncertainty. Now I've chosen to plot my histograms as a function of distance. The students could calculate the equivalent reaction time based on these distances and plot their histogram in terms of the reaction time as well. The criteria we're using for the standard deviation, we can either use the standard deviation that we calculate based on the 20 values, probably using Excel to calculate it exactly, but we can relate that to the meaning of this histogram by noting that within one standard deviation on either side of the mean, we should have 68% of the data. And so if the students take 20 data points, that would be 14 of the points should lie within the mean, or within the uncertainty of the mean. So you can have them check that based on their histogram.